Hi everyone, my name is Kevin. I'm a member of the 2024 Risk Cohort. Over the summer, I worked on a hierarchical framework for safe collaborative manipulation via Game-Theoretic responsibility allocation. Let's start with a motivating example. Suppose you and someone else want to clean up a cluttered kitchen table. How do you choose which objects to pick up? Once you choose an object, how do you decide how to safely move within your environment? As humans, we make these kinds of decisions intuitively. We intuitively choose which objects to pick up, and we intuitively move within our environments safely. However, by default, robots don't have these kinds of intuitive systems, nor do they have explicit reasoning capabilities. Thus, our project is on enabling robots to make safer decisions by providing a robot with a way to explicitly reason about the decisions they make in collaborative scenarios, using notions of safety and responsibility. Let's go over some related works. Our method is inspired by a paper on multi-robot task allocation, which used cooperative game theory to associate agents with tasks. We perform this association using a collision risk-based notion of responsibility, which accounts for the intentions of the human collaborator. Recent work also formulated a control barrier function for robotic manipulators. We draw from this work to provide safety guarantees over low-level motions. Additionally, to enable the robot to regulate its low-level safety strategy, we draw from recent work in control barrier functions, which allows individual agents to maintain pairwise safety based on the collision risk each agent faces. Lastly, we use a problem setup similar to recent work in value alignment in human-robot interaction. This allows our robots to infer the intentions of a human robot and of a human collaborator. Overall, the existing safe control methods only consider safety over low-level motions. However, robotic manipulation is different in that decision-making is innately hierarchical. We have a discrete set of high-level actions, which are which objects to pick up, as well as a continuous space of low-level motions, which is the joint space. Our project proposes a hierarchical framework to enable a robot to make safe high-level decisions and regulate its low-level safety strategy based on its belief in the intentions of its human collaborator within collaborative manipulation scenarios. Let's go over the problem setup. As you can see, we have two manipulators in the scene. The left one represents the autonomous agent, or the robot, and the right one represents the human. The objective is to place all objects in bins safely and efficiently, where each agent is assigned a specific bin. In terms of specific mathematical formulations, this task is modeled as a two-player Markov simultaneous action game. Additionally, the human agent has preferences as to which objects should be prioritized. In the kitchen example, this might correspond to a spill on the table, which should be cleaned up before it spreads. Thus, the robot should infer these preferences so as to best complete the task. The human's preferences are modeled as a non-parametric reward function. As you can see in the slide, we have 4 different colored boxes. The non-parametric reward function assigns a value to each box color. To infer the human's intentions, we use a Bayes filter update rule. This updates the robot's belief using the probability it believed the human collaborator had of performing the action they actually performed. Moreover, we use the Boltzmann decision-making model, which allows the robot to map the game state in human action, given its own belief, to a probability of the human taking that action. This model defines rationality as the degree to which a human chooses higher valued actions over low valued actions. The variable beta determines the actual degree of rationality. Higher values of beta imply that the robot believes the human is more rational, and vice versa. U here denotes the utility function that the robot believes the human is optimizing. In terms of low-level motions, we use control barrier functions, or CBFs, to enable the robot to maintain safety. CBFs provide an admissible control space, such that if a control from this space is executed, then the system will remain safe. This is called the forward invariance property. We choose CBFs because they can be formulated such that the joint admissible control space for a system with 2 agents can be partitioned. The result of this is that individual agents can maintain pairwise safety. We consider the kinematic model of robotic manipulators, where the control input is the joint velocities. As you can see here, the top inequality is a centralized constraint considering the velocities of 2 agents, whereas the bottom constraint is one that only considers the velocity of 1 agent. Additionally, there is a local responsibility share omega sub I, corresponding to the responsibility share for agent I in maintaining the pairwise safety. On this slide, we have a proposed hierarchical framework. As you can see, the human intention learning module informs the safe decision making, which then informs the responsibility aware CBF. The result of this is that the robot is able to use its belief about the human intentions to make safe decisions and regulate its low-level safety strategy. Our method is inspired by recent work in multi-robot task allocation. We use cooperative game theory to associate agents with actions based on a notion of collision risk. In a cooperative game, players can come together to form coalitions. A cooperative game is defined by the set of players N and the characteristic function V, which assigns a value to each coalition. In our project, we introduce a characteristic function based on a notion of collision risk. One such coalition might consist of the robot as well as actions 0, 1, and 3. This would correspond to some scenario in which the robot believes it's responsible for these actions. Note that in our context, a valid coalition must have a single agent. To allocate actions between itself and the human, the robot finds a partition that has the least aggregate risk posed to all agents. An action allocation essentially partitions the actions between the players. One example partition in a game with 6 actions that are 0 indexed might associate actions 0, 1, and 3 with the robot and actions 2, 4, and 5 with the human. This would correspond to some scenario in which the robot believes it's responsible for actions 0, 1, and 3 and the human to be responsible for actions 2, 4, and 5. Recent work formulated a CBF for a kinematic model of a robotic manipulator. One type of collision handled in this work was self-collisions, which are undesired collisions between links of a manipulator. We can reinterpret this collision constraint as a centralized constraint, considering collisions between 2 links of 2 different manipulators. This constraint takes a special form which allows us to partition it into decentralized constraints. As you can see here, we have a decentralized constraint that considers only the control input of a single manipulator. This then allows our low-level responsibility shares to be assigned such that the robot and human can maintain joint safety independently of each other. We provide proof of safety guarantees in the risk paper. To compute these responsibility shares, we can use Shapley values. Shapley values measure how much a player in a transferable utility game contributes to any coalition it joins. A transferable utility game is a special case of a cooperative game in which agents can transfer utility between themselves without penalty. Within our context, this essentially allows us to measure how much collision risk an agent is subjected to, on average. Once the robot computes the Shapley values for itself and the human, it can perform a softmax over these values to compute responsibility shares. Proof of safety guarantees, given this responsibility share assignment, is provided in the risk paper. We performed a case study to test the impact of an internal representation of human intentions on the robot's decision-making process. Below, we have 3 cases. In scenarios A and B, the robot has no internal representation of the intentions of its human collaborator, whereas in scenario C it does. If, as in scenarios A and B, the robot has no such internal representation, then it needs to make an assumption about how the human will behave in order to interact properly. In our experiment, the robot takes on the worst-case assumption that the human is non-cooperative, meaning that they will not contribute to the task objective. In case C, the robot follows our method to make its high-level decisions. In case A, this assumption is correct. As a result, the robot picks and places all objects in its own bin, and the human does nothing. While there's no safety issue that arises, there is something left to be desired, as the human did not contribute at all. Additionally, this assumption is not always correct, as in case B. As stated in case B, the robot's assumption is incorrect, and the human is actually semi-cooperative, seeking a fair distribution of work between the 2 agents. This causes there to be an overlap between the actions that each agent allocates to itself. When the robot and human reach for the second object, a safety issue arises. Following this, the robot's nominal trajectory any further will lead to collision, so the CBF pushes the robot away. Overall, the task is eventually completed, but the robot subjects itself to collision risk in this case. In case C, the robot has knowledge that the human will allocate itself the middle box. Thus, it allocates the other 2 boxes. This task is completed smoothly with no collision issue. Here is a visualization of some data that we collected. In the top graph, we can see the safety over time in the 3 cases, which is measured by the distance between the agents and defectors. As we can see, there are 2 instances where the end effectors seem to be close, namely in cases B and C. In case B, the agents reach for the same object, which is why you see the distance rapidly decreasing. At a certain point, the nominal joint velocity violates the CBF constraint, So the revised safe velocity pushes the robot's end effector away, which is why you see the distance jerk upwards. In case C, the agents reach for adjacent objects, which is why you see the distance stall at a low value when the agent's end effectors are next to each other. However, there is no collision issue, so nominal velocities are not revised. Additionally, in the bottom graph, you can see that the robot performs best in case C, which is our method, in terms of time to complete the task and distance traveled. This is due to the fact that the robot only had to perform 2 reaching motions, as opposed to 3 in cases A and B. Case B demonstrates specifically where the naive baseline fails. The robot performs an extra reaching motion on the middle block, which could have been saved if the robot knew that the human was going to reach for that object. For our current results, as stated, our preliminary experiments show that our robot's decision-making process can improve the robot's performance in terms of time to complete the task and distance traveled. Our current technical contributions are safety guarantees provided by CVF, a hierarchical framework for safe collaborative manipulation, and a game-theoretic responsibility reasoning process. These all combine to enable a robot to make safe high-level decisions and regulate its low-level safety strategy based on belief in human intentions. Future work includes relaxing current assumptions that we make. Additionally, we would like to further test our method with simulated and human collaborators, use a model-based responsibility reasoning process, and incorporate data-driven motion prediction to allow a robot to plan safer motions. Overall, I'd like to thank my mentors, Yue and John, as well as Rachel and the rest of the RISC community for such a great experience. I've learned so much and have enjoyed my time in Pittsburgh. Thank you.